Cool, good. Hello. Good to see everybody here. So about a year ago, I took absolute leave of my senses and built a database. And then about 5 months ago, we deployed that into production. And remarkably, I haven't been fired yet, which I think was quite an achievement, I guess. So this talk is basically the talk of that build. So why we did this, and then how we did it. You know, more interestingly, what are the technical aspects behind building a distributed database? Conventional wisdom really says that you shouldn't do this. You know, you shouldn't build a database, and you certainly shouldn't try and build a distributed database. It's difficult. There are all kinds of edge cases, corner cases that make it difficult. But I think that wisdom should be challenged from time to time. So, oops, just turn that on. Yeah, excellent. Right, so this is in two parts. The first part is a bit of a justification, so why we did such a crazy thing. So there's a little bit about the product, a little bit about me, a little bit about the company, but only really enough to set the scene. I don't imagine there are any marketers in here, so you're probably not particularly interested in the product itself, so this isn't a sales pitch. And then I'm going to talk about the actual technical details of what kind of goes into your own distributed database. So some brief introductions about me. Yeah, cool. Okay, so I'm a technologist with about 18 years of experience. I'm not a superstar. I've worked in various industries in leadership and hands-on positions, doing data science, machine learning, those sort of things. Predominantly JVM-based, so Java and Scala. I do a bit of Python from time to time as well. And I know about enough C++ to only shoot one foot off occasionally rather than both at the same time. At the moment, I'm a principal engineer at Brandwatch. I do engineering and data science problems across our application stack. I like winter sports, and I like arguing on the internet, and sometimes I can combine the two together, as you might be able to see in that picture there. So, about Brandwatch, very briefly again. So we are a social media monitoring company. We were founded in 2005. We have about 350 employees. Our head office is in Brighton, and we've got engineering teams in 4 offices around the world. We are talking about genuinely big data, so we work with one of the biggest HBase installs in Europe. We've got petabytes of data in there. We work with social media fire hoses, we do web crawling, all of those kinds of things. So, you know, generally quite large amounts of data. We have 3 products, but there's only one that is really of relevance today. And again, I'm only going to talk about this just to give you some context and some background, rather than, you know, kind of go into a sort of a sales pitch. So the product is something called Brandwatch Audiences, and this is all about understanding and finding groups of people online. So we have access to the Twitter fire hose, we create profiles for people, we look at what they're saying, we look at who they're interacting with, and we allow our customers to, you know, to look at those groups of people, to find those groups of people and to break them down and understand what makes them distinctive and different from the background. So this, for example, here is the DevOps audience. I don't think there's anything that's going to be particularly surprising there. Top interest is, unsurprisingly, technology. Who could have guessed? And there's lots of sort of Java-y, team leady, solution architect-y stuff in the sort of things that these people talk about. We also allow you to break down the conversations in more detail. So these are the sort of tweets that people in the DevOps audience send. Again, nothing particularly surprising here, I wouldn't have thought. But this is done against the full Twitter fire hose, so we have quite a lot of data going through this system. And we also allow you to compare audiences against other groups of people. So what makes these people distinctive? What really makes them tick? So that's the product. What problems were we having? So we were having 3 main problems around this time last year. And none of these problems are going to be particularly surprising, I don't think. So the first problem was that everything was getting a bit slow. So we'd reached the inflection point on the scalability curve. When you add more machines to a cluster of services, in our case we're using Elasticsearch for the backend, you know, you tend to see that your overall scalability drops off as you add more machines. You sort of end up spending more time on communications overhead than you do on actually having productive work out of the system. So we were definitely noticing this. Second problem related to that was that it was actually getting quite expensive to run. So this is an accurate picture of our CFO when he saw the last AWS bill. So we were hosted on Amazon. We had a lot of very high-end boxes. We were paying a lot of money. If you're building a SaaS service, typically you want to go for a sort of a single-digit percentage of your revenue for your cost. We were quite a long way from meeting that. Maybe not so badly because, you know, we're talking about quite a lot of data and some fairly sophisticated things that we were doing in terms of analysing that data, but it was still costing an awful lot to run. More problematically was that this was a fairly accurate description of our tech stack by this point. So we'd built this product in 2015. We'd built a nice Java microservices-based architecture. We were practicing CI, continuous deployment. We were using Docker containers, Rancher for orchestration, all of that kind of cool stuff. But our data layer was creaking, and we were adding ever more layers of kind of dodgy hacks to get just slightly more incremental performance out of the system. And when you do that, you know, you accrue a huge amount of technical debt, and that made adding new features and new functionality pretty difficult. So Okay, those are the problems. Why are we having those problems? I mean, not out of this world, are they? So why? Why are these problems? So first of all, to answer that, let's have a look at the data model. So I mentioned sort of big data, and everybody has their own sort of personal definition of what big data actually means. I typically use a definition that kind of encapsulates the fact that you can't keep the working set on a single box, so you need to distribute things around. And we have five main types of data in our system. So we have profiles, so these are kind of Twitter profiles. We have about 500 million of these. They increase slowly over time. New people create accounts, Twitter goes on a mad rampage and kills off loads of botnets, profiles go away. But we do see a lot of updates. So our customers expect to see fresh data in the UI. So if you change your avatar, or if you change your bio description, or if you suddenly gain loads of new followers, they expect to see that in the system. So we see lots of updates to these profiles. And the rate is about 500 a second. So not a huge amount, but not a negligible amount either. Then we have tweets. So we collect all the tweets that people send. We have access to Twitter's Firehose. At the moment, we have a rolling window of about 20 billion tweets, and that's about 3 months. At max, that's about 5,000 new tweets a second coming in, and about the same amount dropping off the end as they kind of expire after 3 months. So again, on its own, 5,000 a second, I mean, that's manageable, right? And then we have shared content. So this is URLs that are shared in Twitter. So we capture all of the URLs, we go and crawl them, we download content. We have about 10 billion of those. Again, it's a sliding window over time, and we see at max about 1,000 of these a second. Followers, so we capture the follower graph, so we look at who's following who. Again, we have access for our Twitter partnership to that. We have about 20 billion records, and these are very simple A follows B style edges. But this is a fixed collection. We only delete edges if somebody unfollows somebody, and the number, again, is increasing over time as we crawl larger parts of the follow graph. And the last and biggest part of this data set is the interaction graph. So we look at who is interacting with who other else on Twitter. So we look at people who are retweeting, we look at whose tweets you're liking, we look at which hashtags you're using, which app mentions you're using, and we create this kind of like this interaction graph that describes behavior. And again, this is a sliding window, but we have about 50 billion records in here, and we see it at max about 10,000 a second coming in. So in aggregate, maybe 100,000 new records a second. Something like Cassandra would cope with that sort of Firehose quite well. This data does change quite a lot. The thing that makes it tricky, and the thing that gave us a lot of problems, was that we allow people to create fairly complex, arbitrary nested queries that kind of join all of these data sets together. So I can find people on Twitter who are following Donald Trump, who have tweeted certain subjects in their tweets, who have maybe interacted with other people, and kind of mash all this data together. So suddenly you're doing these kind of complex multi-way joins across billions of entities, and that becomes quite expensive. So what could we do? We'd reached a point where the current architecture wasn't able to cope. Now, I think we did what any diligent engineering team should do, and that's considering all of the potential options. So we looked at 20, 25 off-the-shelf open source and commercial databases, things from Elasticsearch with a new data model through to MemSQL, which is very impressive but very expensive. This was incredibly tedious. We ended up making a short list of 6 or so. We created real clusters on Amazon. We loaded in terabytes of data. We performed performance tests. We compared it with the existing system. And unfortunately, nothing really worked. Everything had a problem, whether it was lack of sort of free text search support, whether it was lack of graph search support, whether it was just a sheer inability to do distributed joins. So we were kind of stuck. There wasn't an easy, obvious solution to our predicament. So what options did we have? Well, there were 3. So the first was to materially change the way the product works. So Audiences is a very real-time product. You can go in, you can create a query, you can play with the data. Our customers like it. It's very kind of immediate, and you see stuff changing all the time. So maybe we could get rid of that need. Maybe we could sort of have a batch-based process where you kind of create a query, you get some results back in 30 minutes. It takes away the sort of the need to do all this sort of joins in real time. But this is obviously a materially worse user experience. So this was like the ultimate worst-case fallback option, one that we really wanted to avoid. Second option, which was better, I guess, but still not fantastic, would be to just drop some of the functionality. So maybe we could bulk index everything once a week, still allow these joins, denormalize everything into these massive records. But the practicalities of that were pretty troubling. That's quite a lot of data that you need to reindex weekly. And again, our customers like to see up-to-date data, so getting rid of that would be a bit of a step backwards in product terms. So the final option, and the option that we chose for, and the option that sort of was the genesis of this talk, was to build something custom, which is exactly what we did. Excuse me, I should say I've been suffering from a heavy cold, so excuse the water breaks. Right, so option was to build something custom, which is exactly what we did, and that thing we called Mnemosyne. Yeah, she looks happy, doesn't she? So Mnemosyne is the goddess of Greek memory, or the titan of Greek memory, I should get that right, in Greek mythology. It's surprisingly hard to say that word. We only really realised it after we'd created the GitHub repository. And obviously by the point you've done that, you're committed, right? I mean, not going to create a new one. On the plus side, the whole company can now say it, so that's pretty cool. The reason for choosing this is obviously because being the titan of memory, that's pretty applicable to a sort of database. But one of our contributors, who happens to be sitting in the front row, likes to give even the most trivial libraries very grandiose names from Greek mythology. So we had to sort of one-up that, and titans, I think, beat gods. I'm not sure. So Mnemosyne itself is a distributed, horizontally and vertically scalable shared nothing indexing and query layer. So basically, it's kind of like a database that's been exploded and with just the kind of the querying and indexing part. So actually, let's look at the technical details of what goes into building this sort of system. So I'm going to start with the design principles, because this is clearly a huge problem space, right? There are all kinds of products, all kinds of companies, all kinds of people building distributed databases. And we had quite a short time period to do this in. We didn't want to sort of, get lost in the weeds. So we came up with 5 design principles that feed throughout the system. I think would be applicable if you were to do the same thing yourselves. So the first design principle is to know your data. So we're not talking about banking data. If we lose a tweet, it's unfortunate, but nobody's going to die. People probably won't even notice. So we can be a little bit loose about this sort of thing. We can be a little bit loose about data consistency. We can be a bit asynchronous. We don't need to worry about transactions and those sort of things. So we know our data very well, and we know the properties it has. We know how you query it and how it's related and the rate at which it changes. And that allows us to make certain decisions about how we structure things. The second design principle is to not reinvent the wheel. So I'm an engineer. I really love building stuff from scratch. I love implementing algorithms from scratch. It's one of those things that really sort of personally appeals. But that doesn't deliver value to our end users, right? Delivering a product is what delivers value. So I had to rein in the natural instinct to do that, and wherever possible, use off-the-shelf libraries. And the same sort of applies to languages and stuff as well, right? So maybe actually building this in Go or C++ would have been like the ultimate thing to do. But we're a Java shop. We use the JVM a lot. We're very familiar with building high-performance Java apps. So we built this in the JVM. And it's not a crazy idea because things like Cassandra are built in Java and run the JVM. So, not too terrible. So don't reinvent the wheel. Wherever possible, reuse and rebuild on what other people have already done. Third design principle is to keep it simple. So again, temptation is to build this amazing kind of castle of amazingness, database, fantastic stuff, and just keep on adding features. But, we don't need to do that. We know what our use case is. We know what our requirements are. Just keep it all simple. Keep it constrained. Fourth design principle is to know our users. So this is quite key. So our user base is B2B. So we're a B2B company. We sell to businesses. We have a relatively limited number of customers. We're talking like hundreds and thousands, not tens of thousands and millions. And we know that they're distributed globally. The number of concurrent users is relatively low. And that allows us to make decisions around how we structure things. So we can optimize, in our case, for example, to run a query across an entire cluster of 1,000 CPUs instead of optimizing 1,000 CPUs to run multiple queries. If you're doing the same thing, your use case may well be different, and that will lead you down a different path. And the last design principle is to know your hardware. So as part of this project, we move things into a data center. So some of our other products are data center based. We have a heavy investment in ops people, data centers, networking, interconnects, all that sort of stuff. So in our case, it kind of made sense. It didn't really move the needle on the CapEx and the OpEx. But it meant that we could buy boxes that were more closely suited for the sort of requirements that we have, like memory to CPU ratios. And in the end, we actually ended up saving quite a lot of money compared to running this on Amazon, even including for the cost of having people to look after it. Right, so on to the technical details, which is the best part of the talk. So this is a high-level architectural diagram of Mnemosyne. So as I said, Mnemosyne is a vertically and horizontally distributable system. So there are multiple Mnemosyne nodes, which I'm going to try and use as a laser pointer. Yep. So this is a Mnemosyne node. There are many of those. We have 20 in production at the moment. And these basically know nothing about each other. They just know about their bit of the world. So they look after a chunk of the data. Inside a Mnemosyne node, there's the usual database sort of things. So there's a query optimizer that works out how to run queries. There's an aggregation framework that works out how to execute aggregations, summary views of data. There's a CUDA acceleration library that basically offloads stuff onto GPUs to speed things up. And there's a whole variety of indexes that allow us to solve different types of querying kind of problems. In the front of that, there's a gRPC API, which is Google's protobuf-based API layer, which is fantastic. I recommend you have a look at that. And then sitting in front of that, the only thing that knows about other Mnemosyne nodes is the query proxy. And so there's multiple query proxies, and they basically coordinate execution of queries across multiple nodes and then stitch the result sets back together. So that's only the only thing that really touches other Mnemosyne nodes. Data gets into the system via Kafka. So I'm going to cover some of those points now. And the way I'm going to frame it is to talk about the problems we had to solve to build this. So we're going to look at getting data into the system and keeping it there. It's kind of like, I guess, fundamental prerequisite number one of building a database. Then we're going to look about how we model it. So how can you actually build a data model that describes your data set? Then we're going to look at how you can store it efficiently on disk and in memory, because this is quite key. And then we're going to look at actually how you can query it. So how can you find data? How can you access it? And then finally, we're going to look at how you can aggregate it. So how can you build summary views over large data sets? So to start with, let's have a look at data ingestion and storage. So this is like the key. How do you get data into your system? How do you keep it there? So there are sort of three subcomponents here. There's resiliency. So how do you build a system that is able to cope with, say, a node dying, somebody kicking out a network cable, there being a network partition, one data center dropping offline, whatever? How do you make your system resilient to that? Relatedly, how do you make it fast? So we, in our case, know exactly what sort of rate of change, new data coming in that we've got, and what sort of queries are being executed. How do we cope with that sort of load? And how do you cope with load that we might have in the future? So how do we sort of build something that's quite good for now, but not over-optimized for the current use case and can cope with new stuff? And then how do you build a system that can scale? You know, how can you add more nodes to your system and then not have this same early scalability sort of drop-off that we saw with our pre-existing system? So the first part of that is what to store. Right, so you think about a database, you think about fully fledged records, right? So here's a JSON blob, or here's a row in a relational database, and it's got loads of columns in. So we realized quite quickly that actually we don't need to store the full record. If you look at our UI, you look at our application, there are lots of fields that are only relevant to the UI, like the avatar URL. Nobody's ever going to query from the avatar URL, but it's quite an important part of the user experience when you look at it. So we don't need to store that sort of thing in Mnemosyne. We only really need to store the data that's needed to execute and answer queries. So that was kind of like realization number one. And by doing that, we can push off like the tricky distributed data storage into a system that's already been built. In our case, we're using Cassandra and MongoDB. Others are available. So the whole third-party key value store thing basically means that Mnemosyne itself just returns primary keys of entities. So you execute a query, you just get back a list of primary keys. And then you need to then pull those out of a third-party key value store, which works very well for our use case. So how to be resilient? Building a distributed database, and there's really one way of doing this that makes sense, and that's to replicate data, so to keep multiple chunks of data around. It's certainly used everywhere. There are other alternatives that are less popular, but this is what we did. So we replicate data. You can keep from 0 to n replicas. That's how resilient you can be. Next one is how to scale. And this is also kind of related to knowing your data. So our data model is incredibly easy to shard. So all of our queries are executed in the context of a user profile. So you do a query, and it's all around the user. So you can shard on the user. And we have 500 million user profiles. So in theory, we could shard 500 million times. And we can treat each of those shards completely separately, which is great, because that makes it very easy to scale. We just have multiple shards that just lie around on multiple boxes. Again, nothing particularly revolutionary there. That's the sort of model you'll find used all over the place, but it works out quite well for us. Okay, so we have these Mnemosyne nodes, we have these key value store nodes, that's a third-party key value store. Where are we going to actually store the record of truth, and how are we going to get data into the system? So we're going to use Kafka. Who uses Kafka in here? Yeah, at least half the room. I'm not surprised. So Kafka is like the success story of the sort of big data world, open source big data world. Everybody uses it. It's incredibly battle-tested. You can use it as a distributed source of truth. It's a distributed log. It stores key value pairs in a log structure, multiple topics. And we use that as our underlying source of truth. So when we want to populate Mnemosyne, or when we want to populate these key value store nodes, we just pull data out of Kafka. And if we want to change our schema, we just pull data out of Kafka. And that immediately takes away a lot of the sort of complexity around durability and ensuring that the right version of a record is in the right place, because Kafka just looks after that for us. So if you remember back to our data model or our entities, we have two types of collections. We've got these sort of persistent collections that are like relational tables, where you have some entities that just stay around until somebody actually explicitly deletes them or adds to them. And then we have these sort of windowed collections, so this sort of time window, like 30 days, 60 days, 3 months, whatever, of data that gets expired automatically after a period of time. And both of these map quite naturally to the way Kafka works. So compacted topics work very well for these kind of persistent topics of data, these persistent buckets of data. So I'll work you through an example. So if you imagine this is a Kafka topic, and somebody's put profile 1 in, maybe it's got a key that's the profile ID, and then somebody's put in profile 2, fantastic, profile 3 appears, so far so good. Oh no, somebody's added a new version of profile 1. Remember, this is a distributed log, so you can only add things, you can't modify things in place. So maybe profile 1 has changed his avatar logo, maybe he's just expressed his love of Trump, I don't know. but there's a new profile that's popped into the queue, into the topic. So we now have duplicated data, which is not ideal. And then, oh no, profile 2 turns out to be a Russian bot. So Twitter have killed it, and the profile's gone away. So it's marked as deleted in the log. Again, it's a distributed log, so it only contains updates. It doesn't contain modifications to data. So now we've got profile 2 that is completely irrelevant, a record that says profile 2 is gone, and 2 versions of profile 1, which is not great. And oh look, somebody's added profile 4. So now we've got like 50% wasted space here, which is a problem when you multiply this by 500 million profiles, or 10 billion tweets. So what you can say to Kafka is, I would like you to keep the latest version of all of these key value pairs, and then just clean up the others as and when you can, and Kafka will do just that. It'll compact the log, it'll rewrite the log, and it'll bin out all of the stuff that's no longer relevant. So we end up with a data store that is relatively close to optimal in terms of the amount of storage space it's using, but is also pretty persistent and pretty reliably so as well. So the window data, so these kind of like sliding windows of data for like tweets and events, they're just standard Kafka topics. And a standard Kafka topic contains things, and you can say to Kafka, I'd like you to clean this up after a period of time, and I'd either like you to start deleting old things when the total topic size is more than 6 gigabytes or something, or I'd like you to start throwing things that are more than 3 months old away. So that means, say these tweets are too old, Kafka will periodically go through the log and go, oh, yeah, actually, maybe we should delete those. And then again, you end up with a fairly optimal space usage. So there we go. We've got data coming into the system. We've got a way of it happening quite reliably and of it being distributed around. So far, so good. We haven't really had to invent anything here. This is existing code. This is Kafka. Fantastic. How do we start to model our data? So the data model. So you might get a theme here. So we haven't really invented anything particularly new here. We've got kind of a mashup of a relational database and a document-oriented store. So we have data sources, which map to Kafka topics. Data sources contain entities of some sort. And a data source itself has indexes, which are used by the query engine to answer queries. And indexes just pull data out of the records and create some sort of view of that. And then we have stored fields. And these are used to execute aggregations. So if you look at like an audience and you want to sort of see what the gender breakdown is, this all works from stored fields. So we'll store for each record a very small piece of data that allows us to execute aggregations, but only the data required for the aggregations, not all the redundant data. And then there are multiple partitions, which basically map to shards, and then all of these live within a namespace. So pretty simple, pretty straightforward. In practical terms, this is a sort of a simplified version of a Twitter profile and tweet schema. So we have a tweet entity, which is this button, yep, which is here. This contains an ID, which is a tweet ID, and the profile ID, which is the ID of the person that sent it. And then there's an index, which is free text index on the body. So it's only storing the index, it's not actually storing the raw body text. And then we have a Twitter profile, which is kind of like the core entity. Again, we have an ID. We have an integer score that's used for sorting. It says how influential somebody is. And then we have a set of indexes. We have a bio, free text index, some sort of location index. Maybe that's a geospatial index. And then maybe we have a bitmap index for gender. So these are all sharded, which means there needs to be some sort of key to sort of work out which shard this data needs to go into. And unsurprisingly, we have a shard key. So in our case, in this schema here, the profile ID is a shard key. So it's the primary key of the Twitter profile, and it's this sort of secondary field in the tweet. So this is quite expressive. It allows us to model relationships. It allows us to model fairly complex data. And it allows us to use different index types in the data as well. OK, so we've got data coming into the system. We've got a way of modeling and representing it. How do we start to store it and access it? So we kind of cheated. So wherever possible, we use in-memory computing. Unfortunate location of the light there. So DDR4 in your modern server has latency about 1,500 times lower than a PCI Express SSD and throughput about 30 times faster. So if you can get as much data as you can into memory, you win, right? You're already ahead. Obvious deduction. Now, you remember we were building this in Java, and Java has a garbage collector, which tends to work pretty well. So, using the heap, great. Allocate objects using new operator. Don't care about deleting them. Garbage collector will clean them up. It's easy to use. There's no manual allocation. It's pretty safe. It's quite hard to, double allocate memory or have dangling pointers that bring the whole system down. Obviously, you can leak memory sometimes. So it's pretty safe. And it's, from a developer's perspective, less complex. I don't have to worry about all the cognitive load of like, did I deallocate that thing over there? But there are two problems with using large heaps in Java. So first is that it's not terribly efficient in terms of space. So if we take this simple example here, we have a string which is 8 chars, exclamation mark. In raw terms, that's just 16 bytes, so 8 2-byte UTF-8 characters, pretty small. But if we store that in Java, that actually takes up 64 bytes as a string. So you have the string object itself, which has some JVM overhead, some access fields, those sort of things. That's about 16 bytes in hotspot. Then there's some bookkeeping data in the object itself. So the string object keeps the length of the string. That's about 12 bytes. There's a pointer that then points to a char array, which contains the actual text. A char array is treated as an object in Java, so there's the additional 16 bytes overhead. And then there's finally the actual data. So this 16 bytes of text has suddenly ballooned. Now, normally that doesn't matter, right? So you're writing stuff in Java, it's about the speed of building stuff, the safety of building stuff. You don't really care about saving individual bits and bytes. But if you're using very large heaps and you want to keep as much data in memory as possible, it actually starts to matter. Second problem, arguably more serious, is that if you point, say, OpenJDK at a very large heap, say 512 gigs, a terabyte, this is pretty much what happens. It gets pretty upset. So it's not really designed for heaps of that sort of size. So you can spend money with people like Azul and get a JVM that's specialized for working with very large heaps, but they're pretty expensive, like very expensive. Luckily, there is a way around this, a very commonly used way, and that's to use something called off-heap memory. So off-heap memory is basically a large chunk of memory you reserve off-heap, and you, the application developer, manage allocation and deallocation of that memory yourself. So you're kind of doing what you would be doing if you were writing low-level C code or Rust code or something like that. We still use heap. It's still a garbage collector. It's still where most of our sort of short-lived runtime objects live. But the bulk of the data itself lives in this big region of off-heap memory. In our current setup, we have 256 gigs of off-heap memory per box. So that works pretty well, doesn't it? Well, there are some problems, obviously. So RAM is volatile. Obviously, you turn a box off, the data goes away. But more subtly, if you turn off your application, the data goes away as well. So this is a problem when you're doing upgrades, okay? So you turn off your application, JVM closes down, process closes, heap memory goes, off-heap memory goes. You've probably got this sitting on disk somewhere, right? I'd hope you do anyway. So you start your application up again, and then, oh, look, I need to load 512 gigs off disk. It might be an SSD. That's still going to take 5-10 minutes. It's going to take a while. So when you're doing rolling upgrades, that can be pretty problematic. Maybe you don't want to do that. Then there is a solution, and that's to use something called memory mapped files. So this sounds quite complicated, but what this basically is you say to the operating system, I've got this file that's however big it is. I would like you to map the contents of that file transparently into the address space of my application. And when it does that, the data itself, the hot data, is actually kept in your kernel page cache, not in your JVM. Okay, so if you restart your application like that, all the hot data is still sitting here in the page cache, which is great. So you don't have this sort of cold, hot restart problem. Obviously, this being Java, things aren't quite that straightforward. So this is typically how you would create a memory map region using Java. So you just use a random access file, get the channel, you call the map method. Great, right? Maybe. So then we look at map byte buffer, which extends byte buffer. Got a bad feeling about this. Oh yeah, if we look at byte buffer, all of the offsets and indexes in the byte buffer class are integer-based, which means that you can map per byte buffer a maximum of integer or maxint, so about 2 gigs of data. Well, that's not very good, is it? So the normal solution to that problem is to have multiple byte buffers that each represent different overlapping regions of this file. Again, maybe that can work. But as it turns out, when you're doing kind of like streaming analytics and stuff, all of the logic around checking for boundaries and working out offsets, all this sort of modular arithmetic, actually gets quite expensive. And when you're talking about doing this across, tens of gigabytes of RAM, it actually becomes a noticeable part of your overall runtime. So there is a solution around this, and anybody who saw the keynote this morning will recognize this particular class, unsafe, sunmisk unsafe. I can't think of a more appropriately named class in Java. It's very unsafe. It allows you to do very low-level memory manipulation. You can create pointers. You can do all kinds of like native-style things. You can blow yourself up very easily. It's unsafe. It was going to go away in Java 9, but the open source community said, hang on a minute, you're going to break all of our high-performance Java applications. So at the moment, it's still around. Bits of it are being moved into official Java libraries. If you really need to do very high-speed native operations, unsafe is the way to go. But yeah, as I said, bear in mind the name. Cool, so we've got data in memory, we've got a data model, we've got a way of getting it into the system. How do we start to kind of like query it and represent it for queries? So I'm going to take a very slight diversion at this point into something called the algebra of sets, which is a very fancy name. So a set is basically a collection of things. Doesn't matter what it is. And the algebra of sets basically defines the properties and laws of how these sets can interact. So, like more concretely, imagine you've got a Twitter profile like this. It's 3 attributes. We have a location up here, which is maybe a single value. maybe it's a country code. We have a profession, maybe there's multiple professions because people can have multiple jobs, and then maybe there's interests, and people are obviously interested in multiple things. Great, how do we represent that as sets? What am I talking about? So this is how you can represent it as sets. So you can create a set that contains all the IDs of the Twitter users in the UK, so where the location field is UK. And you can create a set which is all of the Twitter users interested in sports, and a set which is all of the Twitter users who are journalists, and so on and so forth. More abstractly, we can say we have an entity, Twitter users in our case, and we have this thing called a predicate. And basically the predicate puts things into sets. So in our example here, we can have a predicate that puts people into the journalist set, and a predicate that puts people into the lives in the UK set, and a predicate that puts people into the is interested in sports set. And you can see I've got a mistake in my slide there, which is great. The reason why this is a very interesting way of representing this data is that predicates can be any kind of operations. A predicate could be an index, so you could have a nice log structure merge tree or an inverted index or whatever, but you could also have just a brute force scan of data that can do the same thing. So it's quite a nice abstract way of representing how this works. So if we take our 3 sets here, let's say we want to find the Twitter users in the UK who are also interested in sport. Obvious way of doing that is just to find the intersection of those 2 sets, and that'll tell us the people who are in the UK who are interested in sports. And then we can refine it down even further. We can find people who are journalists who are in the UK who are interested in sports. Presumably it'll be a smaller amount of people. Again, it's just a set intersection. The problem comes when you think about the actual mechanics of doing these kind of set operations. So the obvious, straightforward way of doing a set intersection is to find the smallest set and then just loop over each thing in it and then check to see if it's in all the other sets you're interested in. Okay, and then if it is, you can just do something. You can add it to another collection or update a count or whatever. Pretty simple, but when you're doing this with millions and billions of things, it actually becomes computationally quite expensive. You know, even a hash set in Java, which is like, you know, one of the faster data structures in Java, if you have a hash set with 100 million entities in it and you intersect it with another hash set with 100 million entities, this laptop takes about 1.5 seconds. That's quite a long time. Can we make it go faster? So yes, we can. And the solution is this thing called bitmaps. And I'll just take another swig of this water. So with a bitmap, we can do this same 100 million intersection problem in about 8 milliseconds on this same laptop. So you're talking orders of magnitude faster. So what is a bitmap? Well, a bitmap is, I'd say it's probably the simplest possible data structure you can think about. It's just a sequence of bytes, and each byte is either on or off, and you assign some meaning to each byte. So in our case, maybe we say this bitmap here, this represents users in the UK. Cool. And we're going to say that bit 1 represents user 1, and bit 8 represents user 8. And we'll keep that with all our other bitmaps. So we can say that user 1 is in the UK, and user 8 is not in the UK. And we can just extend this. We can add as many bytes to represent as many users as we want. Very simple. But why is this relevant? So the reason it's relevant is that we can do bitwise operations on these bytes. So we can find people in the UK who are interested in sports by doing a bitwise AND on all of the bytes in these bitmaps. Okay, so that tells us these people are in the UK and are interested in sports. Same for ORs. We can do a union, bitwise OR, fantastic, same thing. But the reason why this works very well is that you're suddenly doing 8 bits of work for one CPU instruction. So there's low-level CPU instructions that do bitwise operations. So if you think about the hash set example, you're calculating the hash code, you're looking it up in your underlying hash structure, whether it's an array or whatever. There's quite a lot of overhead there. There's quite a lot of maybe cache misses. There's quite a lot of just CPU instructions being executed. But here, we're just doing a single instruction to do all 8 things. And even better, on modern CPUs, like Haswell and newer, we have the ability to do many of them at the same time. So AVX2 allows us to do it on 512 bits simultaneously. So suddenly we've gone from doing like one operation per 100 cycles to 512 operations in a single cycle, or even less than a single cycle, which is pretty impressive. So it means you can do these kind of set operations at really high speed. So back to Mnemosyne, we use bitmaps in 2 places. So we use them to represent queries. So these are indexes or predicates or whatever. They emit people that are followers of Trump or Obama or Clinton, and they emit people that are located in the US and maybe tweeted about politics. Maybe that's a free text index, whatever. Each of these indexes emits a bitmap that lines up like that, and then we can just do these bitmap operations on all these intermediate bitmaps. And because these bitmap operations are so fast, we can do this in milliseconds, and it means the bounding performance of our system is now basically the performance of our indexes. So how quickly can we build these intermediate bitmaps? We also use bitmaps as indexes in their own right. So we have lots of categorical data. So, professions is drawn from a list of 30-odd professions. We can just store each one as a bitmap. And then we can find people that are executives and sports people just by doing a bitwise AND on those and answer that query in a handful of milliseconds. We can also use it to represent a graph. So remember the follower graph problem. So here we have just an array of bitmaps, and maybe this is profile, and this is the people this profile is following. It's a very natural way of representing that sort of data. But there are problems with using bitmaps, as there always are with all of these things. The first problem is sparsity, right? So this graph example, if we have a bitmap per profile, so we have 500 million profiles, and each profile needs 500 million bits to represent the profiles they might be following. That's 62 megabytes per profile, 62 megabytes times 500 million. It's about 31 petabytes. It's quite a lot. RAM's quite cheap, but it's not that cheap. And actually, if we think about the graph, and we think about it on Twitter, on average, people follow about 200 people, and say we need 4 bytes per record to represent that, we could just store the raw list in about 400 gigabytes, which is a couple of orders of magnitude less data storage. Okay, so surely that's ruled out bitmaps for anything practical. Well, actually, no. So there are ways of compressing bitmaps, so using less space. The obvious way is to use something called run-length encoding. So you've got a bitmap here. It's not so big. There's only 2 set bits, one here, one there. We could encode this 8 bytes of data in 3 bytes by just storing the bits. So this says there's a run of 1, 1, and there's 62 zeros, and there's 1 more 1. So that's 3 bytes instead of 8. Bit of a saving. The sparser your data, the more saving you'll get. But there's a problem here, which is that random access gets very expensive. Typically with run-length encoding, to find a value, you need to decompress all of the preceding values. So if I want to find out whether profile 1 is following profile 607, I have to decompress all of the bits preceding that, which gets to be quite expensive. Luckily, there is a solution, and this is something called roaring bitmaps, which was invented by 4 contributors, Chamby, Lemire, Kayser, and Godin. And they came up with what, I guess in hindsight, is quite an obvious deduction, which is that you can break your bitmap into chunks like this, and you can treat those chunks differently depending on the type of data stored in them. So their chunk sizes are 2 to the 16 bits, so relatively small, and there are 3 ways of storing data in there. So first way is it's a dense bitmap. Don't need to compress it. Can't really compress it. It's probably pretty close to the Sharon limit. Fine. Just store it uncompressed. The next way is just to store a list of numbers, so sort of run-length encoding. So bit 0 is set, bit 63 is set. Cool. And then the third way is to store ranges. So 0 to 3 is set, and 61 to 63 is set. And because these are broken up into chunks, it allows you to do sort of pseudo-random access without too much cost. You don't need to decompress huge amounts beforehand. So the last problem, now that we've solved, well, I say we, now that these people have solved the sparsity problem for us, is to work out how to have a consistent meaning for bit 1 in all these bitmaps. So imagine we have 20 bitmaps for profession that line up. We want to make sure that bit 1 always maps to profile 1, and bit 8 always maps to profile 8. So the way we do that is using something called ordinals. So when we first see a primary key from the outside world, we'll convert it into a monotonically increasing integer. And then we'll map that to a fixed offset in the bitmaps, just like this. So it's a bidirectional map. And then when we want to return result sets, internally we just use the ordinals, and externally we'll convert them back into primary keys like that. Cool. So we've got data in the system, we've got a data model, we've got a querying system, we're using memory and disk pretty efficiently. Last thing to talk about is how we do aggregations. So how do we actually build summary views of this? So this is a problem that seems trivial until you get into the details. So if we look at some example data, so this is event stream for URLs that are shared by people on Twitter. So we see maybe 1 billion of these a day, give or take. It contains a user ID, so this is the person that shared a given URL. This is the timestamp that they shared it in. It's just an offset from the epoch. And then this is a unique ID for the URL, so it's pretty trivial data. But what we do is we take an audience, we find all of the tweets that they've shared, and then we find which of those tweets are over-indexing for that audience. So which tweets have been more interesting for that audience than the sort of the average Twitter audience. And that becomes quite problematic because we're talking about billions of rows and doing this all in real time and joining it together with these audience queries. So there are 2 parts to this solution for this problem. And the first part of the solution is this thing. Anybody know what that is? Yeah, so this is a dice shot of the GP104, which is NVIDIA's Pascal architecture. So anybody who's got a gaming PC or a gaming laptop has got one of these in it. It's pretty cool. I'm not going to go into the architectural details too much here, because that's like a 50-minute talk at least in its own right. But suffice to say that this block diagram kind of shows the complexity inside of here. So we have the ability to execute thousands of threads simultaneously on a GPU. So a 1080 can execute about 3,500 threads simultaneously. There are lots of constraints around the type of memory access you can do, the latency for memory operations, the type of synchronization primitives that are available. But if you construct your problems appropriately, executing 3,500 threads simultaneously on your problem is pretty cool. Obviously, your problem needs to be embarrassingly parallel. As it turns out, lots of aggregation-style problems are. So I'm going to walk through an example of an aggregation here. So we start with a dispatcher, which is a bit of code that lives in Mnemosyne, and this is aware of the fact that the GPU is effectively a computer that's kind of distinct from the main CPU and main memory. So it has its own RAM. It's at the end of the PCI Express bus. If you want to get data from your main system to the GPU, it has to be sent over that same PCI Express bus, whether it's implicitly or explicitly. There's a cost. You have to navigate across the PCI Express simplex. There's a latency there. There's the time it takes to transfer gigabytes of data. So it's quite possible that there's an operation like sorting where with many millions of results, it makes sense to send it to the GPU, but with a few tens of results, it doesn't. It's more expensive. So the dispatcher knows that, and it knows when to execute things locally and when to send things to the GPU. We have multiple GPUs in our systems, so the dispatcher also works out which GPU to send a given task to, and that's based on utilization, memory, all those sort of things. So walking through this problem, this is our data set. So we have user ID, timestamp, URL, and a new column which is shared in, which is the tweets that this particular URL was shared in. So to calculate the top N, we want to find the most popular tweets. We would start by basically just scanning over the data and looking to see which of these rows contains a user ID that's in our result set. Fairly fast, but again, doing it over a billion things can take a bit of a time. So our first optimization is to just change the way we structure the data. So we store our event data in buckets, either an hour or a day, and within those buckets, we organize them by primary key. So in our example here, by the user ID. So we end up with one user ID here, 111231, with 3 bits of data, and then this other user ID here, 332123, with another 2 bits of data. And that means that we have to do far fewer is this set of data relevant to our query style operations. How much operations this saves depends on your data set. In our case, that saves about an order of magnitude lookups, so that's definitely worth having. The next thing we do is ensure that we don't have to look at data that isn't relevant. So in this top-end query here, we're going to find the most popular URLs. We don't care which tweets it was shared in. It's just completely irrelevant. But if we traverse across this data as part of our operations, we're pulling more data across the memory bus. We're doing more damage to the CPU cache. It just slows things down. So we structure things into columns. We put all of these bits of data into separate columns, store them in separate files, and that means we can just disregard data that's not relevant to a given aggregation. Pretty simple, I guess. So here we go. We've selected some users that are relevant to a query we've just executed. We're going to pull out the data, and we pull it out, and we stash it into off-heap memory, contiguous regions, just like that. Just 2 vectors, URL and timestamp. We don't care about user ID anymore. We've already selected the users that matter, so that's irrelevant. Then we send that across the PCI Express bus to the GPU, like so. But there's a problem. Because these are buckets of time, like a day or an hour, a query could be for 3 hours within that day or 10 minutes within that hour. So we execute a filter on the GPU as well, where we filter out records that are not relevant. So we filter this out using a predicate. This happens, again, at massive scale, thousands of times simultaneously. It means that we can basically delete data that is not relevant to our query, like so. We end up with something that's a bit smaller. Fantastic. We don't need timestamp anymore. Timestamp is just not relevant because we've constrained our data to the timestamps that matter. So we can reuse this data, and we can rename it to count and give it a value of 1. Again, this is happening in parallel on the GPU. Anybody that's done any map reduce will recognize this particular approach. We then sort. So we sort the URLs by their ID, which means that we end up with these contiguous regions where the same URLs are next to each other. And again, this happens, a sort can happen to a billion 32-bit integers a second on a modern GPU, so pretty quick. We then run an algorithm that basically finds the boundaries between these regions. So we can see that there's a boundary here between 100 and 101, and there's a boundary here between 101 and 102. There's 2 contiguous 102s, and then there's another boundary here, like so. Fantastic. So the last thing we do is to run something called a reduction, which basically takes all of the values in a region, like so, and then executes a predicate or a function against them. In our case, we're just going to do a sum, and that gives us our final result. So we have URL 100 occurs once, URL 101 goes once, and URL 102 goes twice. And the very last thing to do is to sort it, and that gives us our final result set. And all this happens in milliseconds at great scale on the GPU. So in Mnemosyne, we use CUDA for 4 main things. So we use it for calculating top-end queries, so the sort of aggregation we just walked through. We use it for sorting, so for very large result sets, we can sort billions of things in handfuls of milliseconds. We use it for generating histograms, so show me how active these users have been over time. You want to break that into buckets. That's an easily parallelizable thing that can happen on the GPU. And we use it for bulk filtering as well. So this huge data set, can you tell me what the average, number of followers is, something like that. So to give you an example of how fast this can go, to find the exact top N from a data set containing 100 million events takes about 480 milliseconds on a 1080 GPU. If you're doing it on the main CPU, it'll take about 100 times longer than that. So it's quite a significant win. So we put this into production. We did all of this work. We went to a lot of effort. But was it worth it? So, yeah, I think so. So there are 2 metrics I'm going to use to decide whether it's worth it. So if you think back to the problems, first one was speed. So on the morning of the 23rd of January, we got some baking butties, got some coffee, flipped the switch, and this happened. So, yep, this little thing, which I've helpfully pointed out with the big red arrow, this is where we flipped over, and we saw about a 40 times reduction in query execution time. In fact, the bulk of the green here is now other overhead, like security checking in the API and those sort of things. So we met our performance goals. That was pretty good. Secondary side effect was this thing. So we ended up deleting 38,000 lines of code and only adding 16,000 lines of code, which is quite a lot of technical debt that goes into the toilet, so that was quite good. Simpler platform, easier to use. I should point out that all of these lines were reviewed into this long life branch. I wasn't asking Luke and Adina to review the full branch, because I'm evil, but not quite that evil. So it worked for us. So there are a couple of questions left to answer, I guess. So the first is, can you do it? Absolutely. I'm not a database expert. There's an Isaac Newton quote that is a bit trite that people use all the time that sort of applies here, which is, if I have seen further, it is by standing on the shoulders of giants, which basically means this is only possible because lots of very smart people have built lots of great open source code, whether it be roaring bitmaps, whether it be Kafka, whether it be Mnemosyne, whatever. To reinvent that would take decades. This is only possible because you have all of these fantastically well-supported, battle-tested bits of code that we can reuse in places. Next question, I guess, is, should you do it? Well, I don't know. That's a question you have to ask yourself. I think it was the right decision for us. I think we made the right choice, and I think we did all of our due diligence beforehand. We did these tests, tested things out. So yeah, only you can really answer that question. Thank you. Any questions?
I'm a bit curious about how you implemented the part of CUDA. Did you code in C or?
Yeah, you might remember Maya. So he's asking if we coded the CUDA stuff in C. So yes, so there is some experimental Java CUDA stuff that is kind of getting there, but no, we used C++, which is why I made that reference to shooting my feet off, because it's pretty painful.
Did you integrate it with the Java side?
So that's actually almost like a talk in its own right. So the obvious way to do it will be to use JNI and JNA and do it that way. This stuff is a little bit unstable, so it's quite advantageous not to lose your entire JVM and all your business logic and hot data. So we actually use shared memory, and we send things to shared memory, and then that gets shuttled across the bus, which keeps things quite stable.
Just as to continue the same question,
Mm.
and talking in terms of your story about off-heap operations and using unsafe, I have like rather provoking question: why Java then?
No, that's a good question.
Might do the same with like not fighting with GVM and for memory access.
No, that's a reasonable question. So he's asking whether it would have been better to have done this in something that wasn't Java, so there isn't all this fighting with the JVM and garbage collection and that sort of thing. So with more time, if we had more time available, yeah, probably. But we're very familiar with Java. We had quite a tight time boundary, time pressure. So yeah, I think it was the right decision. I have plans about that, which I haven't really shared with anybody yet, but Luke's thrilled, as you can see. Cool. Thank. Yep.
Pretty much same question. Have you considered libraries like Joggle for that purpose?
Yeah, so Joggle was one that obviously came up as being a sort of a CUDA/OpenCL style Java thingy. It doesn't have the operations required for the sort of, you're talking about very low-level CUDA style operations. So we actually started out using something called ArrayFire, which is a C-based library that's quite a high-level GPU and CPU agnostic way of accelerating parallel operations. But the problem there was the same sort of thing where if you can fit what you're doing into it, it's great, but if you want to do stuff that's not built into it, it becomes quite painful. So we ended up just using the sort of fairly low-level CUDA stuff. We sort of thrust.
I understood how like matrices stuff works and why it's really fast, but I have a question about the sets and how do you create them ad hoc. I mean, if let's say user type all the tweets with evokes UK hashtag, so do you create this data set like ad hoc and how much time does it take?
Yeah, so for stuff like free text search, we just use Lucene, and we index things based on their ordinals rather than their sort of external primary keys. So we use Lucene's, what's it called? Kind of off-heap field stuff, basically, to accelerate that. But we do generate those things at runtime. For categorical data, so things that are drawn from fixed lists, like professions and interests and those sort of things, where there's only like 20 or 30 of them, we pre-compute them. So we keep bitmaps in memory that we update as we see data. But that's not really practical for the sort of the free text stuff. Yeah, that's a good question. So two reasons. One is that like enterprise level support is much better with the NVIDIA stuff in terms of sort of support. But AMD are getting there, so the Vega stuff is kind of getting there, and the tooling is just better in AMD land. In NVIDIA land. So if you look at NVIDIA's kind of CUDA IDE, which is based on Eclipse, it has lots of profiling and stuff built in. At the moment, it's just a better developer experience. I imagine that will change over time. Cool. Thank you.